We present LaTeRF, label and text-driven object radiance fields. In this work, we enable extraction of photorealistic object representations from real-world scenes with sparse annotations. To begin with, let's talk about the inputs of our model. We first need to know the general look of the scene. So like other neural fields works, we ask the user to provide a set of captures from the scene including the object of interest. Provided scenes potentially contain multiple objects, so additional guidance towards the object is needed. Ideally, we want these interactions to be sparse and in 2D, since it's less intuitive for users to interact with 3D scenes. We ask the user that for some of the views, click on a few pixels on the object of interest. These are our positive samples. In addition, the user provides negative samples, which are a few clicks on the non-object parts of the scene, including the background and the foreground objects. In order to handle the occlusions, some sort of additional semantic is needed for the object of interest. We ask the end user to describe the object of interest in a piece of text. LaTeRF combines all of these inputs and provides the 3D representation of the object as an object radiance field. These 3D assets can be used in applications such as AR and VR, photorealistic simulators, and content creation. Now let's talk about how the training is done. The conventional NeRF MLP is extended such that in addition to the color and density for every point in the space, it returns an Objectness Logit which is proportional to the probability of that point in the space belonging to the object of interest. The colors are rendered using volumetric rendering same as in NeRF and are used to calculate the reconstruction loss. For finding the Objectness Logits of the rays, point colors are replaced with point Logits. For every annotated pixel, the Objectness probability of its corresponding ray, which is the sigmoid of its Objectness Logit, is supervised using the binary cross entropy loss. For inpainting the occluded and missing regions, we propose the differentiable object renderer. It enables us to softly filter the points that are related to the object and render the object without having to retrain a NeRF. Random rendered views of the object are then compared to the piece of text in order to calculate the clip loss using a pre-trained clip model. Here is a summary of our training pipeline. While the overall scene is supervised using the input images with the reconstruction loss, the sparse pixel level annotations are used in the classification loss to supervise the Logits. Using the Logits, we softly filter the object and pass it to the clip model alongside with a piece of text in order to increase their similarity and inpaint the missing parts. For real-world scenes, we render the object masks and use them to filter the potential cloud artifacts. Experiments and ablation studies. Since for numerical evaluations, the ground truth objects are needed, we use Blender to create a synthetic dataset. Our scenes contain ground truth object masks that are used to sample positive and negative pixel level annotations. Our results show that while the classification loss guides the model towards the object of interest in the scene, the clip loss is filling the unobserved parts. However, setting the weight of the clip loss too large makes the renderings less consistent with the object in the scene. Our experiments justify each of the design components while showing superior performance to the baseline. We mitigate the need for a large number of pixel labels by showing the importance of the labels sampled around the boundary of the object. Please check out our codebase, which further combines depth-supervised NeRF and instant NGP for faster convergence. Thank you very much for your attention.